Okay, welcome to part 2 of lecture 5. We're going to finish our discussion of confidence intervals. So, how do we interpret the confidence interval? Well, it ties into the fact that this is also a random variable. Well, also a random interval. So we have to be careful when we think about it prior to and after the experiment. If we select n samples at random each time, we're going to get a different confidence interval that we observe each time, right? Because this is also a random quantity. So after we run it, the 1 minus alpha 100% of the resulting confidence intervals will actually contain the actual mean mu. That's what we can say before we run it. And if you ran it infinitely often, this is what would happen. However, any one particular confidence interval that we observe either has the mean or it doesn't. So this is why we can't say for a given observation we have a probability that this given confidence interval that we observe has the mean. It's that prior to it, the process we're running will have that probability. So this is the subtle bit. Is this statement here is what we can say. We can say that we are confident that the confidence interval that we are using contains the mean with that probability. But you can't say when you're given it, when you observe it, that the observed confidence interval has it. Because if you think about it, the observed confidence interval either has the mean, or it does not have the mean. Okay, so in some sense, this is like the capital unobserved CI. And then the wrong interpretation would be the given observed CI. Okay, that one, either it has the mean or it doesn't. Whereas before we observe it, in theory, it has the probability of containing the mean. Please ask me if you have any questions about this. I think this is one of the hardest and most subtle ideas that we discuss in this class. Okay, so with that in mind, now we want to think about, well, how do we improve our confidence? How do we get more confident that we have it? And how do we use what we can control, which is really the number of replications we run, to reduce the size of our confidence interval? So let's look at what our confidence interval looks like. So for this example, let's just suppose we want to get a confidence level of 95%. That's a pretty common thing. Common levels are 90%, 95%, and 99%. These are rules of thumb levels that are often thought about. And we want our estimate mu to be within 0.1 at a confidence level of 95%. Okay? So we warm up our experiment with, like, say, 30 simulation runs to compute our observation. And we find that to be 3.2. How many do we need to obtain this 95% level of confidence? Well, we look at our formula that we were given. Okay, so we look at this formula, and we see that the more that we run, the higher n is, the smaller this interval is going to be. And in particular, if we want it to be within 0.1, we can see that we have to calculate this. We can say, okay, well, we can say that we can use this student t statistic for this 30 minus 1 for this warm-up observation. And then we can back calculate out what the lower bound is on n so that we get to within 0.1. And if we do that, the student t statistic at this is basically approximately normal, so that's 1.96. And then we take the square root of the sample variance, 3.2, and we can back calculate out, if you run through the math, that means that we need at least 1229.31, or we would, of course, want to round up. So at least 1,230 replications to have an estimate of mu within 0.1. So if you think about it, we want a half width and of w, in this case 0.1. So we solve the equation. If we want this w, right, you're going to also do the same thing. You just substitute for w whatever width you wanted. Okay, so whatever that width was, you just put it into there, and then this formula will give you the number of replications you need. And of course, you should convince yourself this is the right formula just by manipulating this equation in the same way this equation was manipulated, right? I mean, the basic idea here is that you're going to say that square root of n is going to be greater or equal to t alpha over 2 and s all divided by w, and then you take the square of both sides to get your estimate. Okay, and that's how you would get that. And then you take the ceiling. Remember, this here of, say, some parameter beta, that equals beta rounded up to the nearest integer. Okay, that's called the ceiling. So, does running 1,230 replications guarantee that mu will be within 0.1 for a 95% confidence interval? In other words, are we guaranteed that this works? Well, let's consider the half width. The half width is this feature here. Remember, that's what you subtract or add to the sample mean in order to get the upper and lower bounds on our intervals. As n increases, it is true that the student t declines slightly. Certainly, 1 over square root of n declines slightly, so these are happy. But the thing that's unhappy is this. The sample variance could either increase or decrease. So depending on how our variance is changing with an increase in replications, it may or may not be within 0.1. So this is really the cautionary note. This is why it's not as simple as to just say, well, you just run more and you're all good. You actually have to start observing what is going on with the sample variance. Is it increasing or is it decreasing? So it actually turns out that when you start running simulations, you have to understand the stability of your system. Sometimes the system is not very stable, and then your sample variance is going to fly around a lot. You have to be careful when that happens.